all the circuits we've built so far have been built using wires like this. Or sometimes we've got longer ones, sometimes we've got shorter ones, but we've just treated them all the same. And we use them because they are electrical conductors. They conduct electricity. But do all wires conduct electricity equally well? And that's what I want to test out today. And here I've got 3 different reels of wire, and we're going to compare these to see what factors affect how well they conduct electricity. Now, I have 2 different types of metal. I have this one, which is copper, and this one, which is an alloy called constantan. I also have different thicknesses of wires. This is also constantan wire, the same as this, but they're different thicknesses. This is very thin wire, and the way we measure wire thickness is something called SWG, and I don't know if you can see that there. It says 34 SWG, standard wire gauge. 34, the bigger the number, the thinner the wire. This is 24 SWG, and it's a much thicker wire. This reel of copper is also 24 SWG, so these thick wires are the same thickness but different materials. And so we're going to compare how changing the thickness of the wire affects how well it conducts electricity, and we'll do that by comparing a thin wire and a thick wire. We'll compare different materials, so we'll compare 2 wires that are the same thickness but different materials. And one third thing that we'll compare is the length of the wire, and we'll see, does having a long wire or a short wire affect how well it can conduct electricity. And to do that, we're going to connect up a simple circuit with a light bulb. So here I've got a simple circuit, and if I touch these 2 wires together, you should see the bulb lights up. We're going to put our test bits of wire between here, and we're going to compare the brightness of the bulb. To hold the wire in place, we'll use some crocodile clips. Now, it might be quite tricky for us to see, is the bulb brighter or is it dimmer? So to make it a little more scientific, we're going to put in an ammeter, and we're going to measure the strength of the current. So now when the circuit's complete, the bulb lights up and we get a current reading. And as you should remember from previous lessons, the bigger the current, the brighter the bulb. So what we're looking for is, what is the best conductor? If something is a better conductor, the bulb should get brighter and the number should get large. The worse a conductor it is, the lower the number and the dimmer the bulb. You can find this on page 29 of your notes, and the title is Resistance. Resistance is the property of a wire that restricts current flowing through it. If we think back to what current is, it's a flow of free electrons moving through the wire. But electrons aren't the only thing in a bit of wire. Inside the wire, which is made of a metal, there are other atoms. And the electrons can go from atom to atom to atom. And as they do so, they collide. And when they collide, they lose some energy. That loss of energy is what we know as resistance. The more energy that's lost, the bigger the resistance for a certain length of wire. So what we're going to do first of all is we're going to compare the thicknesses of wires. I'm going to use a thin wire, this 34 gauge wire, and a thicker wire, a 24 gauge wire. To make it a fair test, we need to make sure that they both have the same material. They're both made of this alloy constantan, and they need to be the same length. So I'm going to cut about 50 centimeters of this bit of wire. In fact, I'm going to cut a little more than 50 centimeters. And as long as I put the crocodile clips on 50 centimeters apart, that'll be okay. So I have my 2 lengths of wire, and each wire is just over 50 centimeters long. I'll start off with the thick wire, and I'll clip those 50 centimeters apart. There we go, and we can see we've got a complete circuit. The bulb's lit up, and the current is reading 0.24 amps. So it's a little bit lower than it was when we pushed it together. So 0.24 amps, and we can see the brightness of the bulb. I'm going to repeat it now with our thin wire. There we go, we've got a complete circuit. And we can see the bulb's a little bit dimmer. It's maybe hard to see here, but we can definitely see that the current is lower, 0.21 amps. So that's telling us that the thinner the wire, the less current can flow. Don't forget, we've got the same voltage. The batteries haven't changed. So the less current, which means this has got a bigger resistance. Thinner wires have a larger resistance. So we can record that in our notes. We're asked, is the thin wire bright or dim? And the thick wire, is it bright or dim? Well, the thin wire was dimmer, so we'll say dim. The thick wire had a bigger current, it was bright. Now we're asked to consider how the length of the wire affects the resistance. To do that, I'm going to use a long wire. I'm still going to use my 34 gauge Constantan wire, the thin wire, and I'm going to use about 1 meter of that for the long wire. For the short wire, I'm going to just use about 10 centimeters length of that. So I'm going to measure out 1 meter of wire. And so there's our 1 meter of wire. And we can see that the current is lower. It's about 0.15 amps, 0.14 amps. We should also see that the bulb is significantly dimmer than it was before. Let's shorten this wire up to 10 centimeters and see what happens. And when it's 10 centimeters long, we can see it's 0.25 amps, and a bulb is much brighter. So the longer the wire, the less current can flow. So the longer the wire, the greater the resistance. So the long wire was dim, and the short wire was bright. We can use a device that uses this principle to adjust resistance, and that's using something called a rheostat. Here's a rheostat. And a rheostat is very simply a coil of wire that we can connect wires into in a few different places. We can connect it in here, or here, and here. In reality, I'm just going to use this terminal and this terminal. And as well as this coil of wire, it also has a thick beam of wire here, and this bit can slide across from left to right. So let's hook this up and see what happens. So we can see here that the bulb is quite dim, the current's 0.2 amps, and as I slide this, you should see the current increase and the bulb get brighter. As I go back down again, the bulb gets dimmer and the current gets lower. So how does that work? The current flows in this wire and travels along this top thick beam, down through the slider and along the rest of the coil. So if it slid to this end, it has to go through a short bit of the thick beam and a long coil of wire. So that's like using a very long thin wire. If I slide it to this end, it takes a route down this big thick beam, which is a very low resistance, down and only through a very short bit of wire. So effectively this is lengthening the wire, shortening the wire. And we can see that we're able to adjust the current. This is called a rheostat, but it's also known as a variable resistor because we can vary the resistance. So looking at our notes, let's use the variable resistor to complete the circuit, move the slider to make the wire shorter and longer. And again, we can see that a short wire was bright and the long wire was dim. So for a summary, for the same length of wire, something wire has more resistance than something wire. We're looking for the idea of thick and thin. The higher the resistance, the less current. That was the thin wire. So for the same length of wire, Thin wire has more resistance than thick wire. This means as the wire gets thinner, the bulb gets dimmer. As the wire gets thicker, the bulb gets brighter. Changing the length of resistor wire can also make the bulb brighter or dimmer. The something the wire, the brighter the bulb, we saw that was the shorter wire. Where do we see resistors like this in everyday life? Can you think of anywhere in your house that you have something that you slide or more likely turn, and it can change something? We could have things like a dimmer switch for a light. Maybe you've got a room where you can increase or decrease the brightness of it. We can speed up or slow down motors. Volume controls are similar like this. So those are some different uses of variable resistors. On page 31, it suggests that we try doing this with different materials of wire. So this is what we'll do. I'm going to use our 50 centimeters of constantan wire, and I'm going to cut 50 centimeters of copper wire. Now, because I've got the thick wires here, we're not going to see a huge difference. So I'm going to change my settings on my ammeter to allow us to make a better comparison. I've changed the setting on the ammeter here to give a more sensitive reading, and we're going to try our 50 centimeters of copper wire first. I'm getting a reading of 0.255 amps. 0.255 amps. Let's replace the copper wire with constantan wire. Okay, and we can see that the current here is about 0.244. It's close, but it's a little bit lower. And that's because constantan is not as good a conductor as copper wire, or copper has a lower resistance than constantan. This is why we use copper in electrical circuits, because it's such a good electrical conductor. We can write this down in our notes. Which substance has the greatest resistance? Constantan has a greater resistance than copper. There's a little bit here covering what I mentioned a few minutes ago about what resistance is. So as we walk down a corridor in school, occasionally you bump into people, you slow down as that happens. That's very similar to what happens to electrons. Electrons bump into atoms and they lose some of their electrical energy. That's what causes wires to heat up. I'm sure you've noticed that maybe your phone charger heats up when it's in use, and that's because the electrical current is going through the wires, the electrons are bumping around inside, and they cause the atoms in the wire to vibrate more. And that increase in vibration we detect as an increase in temperature. So when a current flows in a solid metal, the electrons collide with these vibrating atoms. They pass on their energy so that they vibrate even more, and as a result, the temperature of the solid increases. This is the source of electrical resistance of the metal and why the current produces heat in it.